As it turns out, redox reactions can be super complicated looking, especially when they're in aqueous solution. If it's just two elements exchanging electrons, it can be simple. But if there's water involved, oh my goodness. And I say, oh my goodness, because often acids and bases, ions, acidic and basic ions are involved. But sometimes you can balance aqueous phase or balance a redox equation with some species in aqueous phase just by inspection. If I know the oxidation state of chloride and it goes to chlorine, and the oxidation state of fluorine and fluoride, then I can sort of easily tell each chloride ion loses an electron to become enter into a bond with another chloride and become chlorine gas. There's two chlorides, each losing one single negative and losing electrons to become chlorine gas, and they're losing those electrons to the fluorine. Each fluorine atom over here gains an electron to become a fluoride ion, but there's two of them. So here the number of electrons transferred is 2, and voila, it's balanced. Well, we better check. Chlorine, chlorine, two fluorines, oh, two chlorines, two chlorines. You also have to check the charges. 2 negatives on this side and 2 negatives on this side. Alright, let me try that again. Here's one. I have a dichromate and an iodide ion in an acidic solution. Oh my lord, what a mess. In red up here I wrote that reminded you of the oxidation states of all these things. It looks like the chromium goes from a 6 plus oxidation state. You should be able to figure that out based on the things we've talked about recently, or perhaps you've watched the video and done some reading. The dichromate's a 6 plus here, and the chromium in the dichromate's a 6 plus, and the chromium becomes a 3 plus ion over here. That's a gain of 3 electrons per chromium, but there are 2 chromiums, so 2 chromiums each gaining 3 electrons, 6 electron gain, and there is an iodine here. It's in the negative 1 oxidation state, entering into a iodate, I believe it is, and that forces iodine into a 5 plus state, and that's a loss of 6 electrons, so gaining 6 and losing 6. 2 chromiums here, 2 chromiums here, 1 iodide here, 1 iodide here. Oh lord, 4 hydrogens here. I'm sorry, 8 hydrogens. Yes, I can see the 8, and there's 4 times 2 is 8 here, and there's 7 oxygens here, and there's 3 and 4 more oxygens here, a total of 7. Oh gosh, what about the charges? This side has 2 times 3 plus is 6 plus and a single minus for a total of 5 plus. This side has 8 plus and 2 minus and 1 more minus makes 5 plus. So this side's 5 plus and this side's 5 plus. So you got to check the charges in addition to just the mass balance. But another common way to balance redox reactions is I call it the method of half reactions, where I go through these steps and trying to balance the oxidation half reaction and the reduction half reaction. Then I go ahead and add them back together to make the overall reaction. Let me not even bore you with reading those steps to you. I'm just going to do a few. So a 10(2) plus ion is oxidized by O2, a 10(4) plus by bromine. So what would that look like? So bromine likes to gain negative electrons. And by the way, you really wouldn't even have to remember or create these, because you'd be given, in most cases, a table of half reactions, and you could look up the half reaction for bromine, bromide, and 10(2) plus, 10(4) plus, and come up with something like this. But if it says up here that the bromine Br2 becomes, it doesn't say it becomes bromide, does it? Well, I guess you got to know that. Back to Gen Chem 1, bromine's in the negative 1 family. It likes to gain electrons to become like that one noble gas just to the right of an electron configuration. I forget. I can look it up. Too lazy. 10(2) plus becomes 10(4) plus. That's a loss of 2 electrons. So this 10 loses 2 electrons to the bromine. Each bromine atom gains 1 electron and becomes bromide. This one's almost too simple, isn't it? I like simple. So there's no water involved here, no oxygens or hydrogens, and I simply write the 10(2) plus becomes 10(4) plus. That's an oxidation half reaction. And gaining 2 electrons, the bromine becomes 2 bromide ions, and that's Br2, 2 bromines and 2 bromines 110 and 110, 2 plus on this side, and 4 plus and 2 minus for a total of 2 plus on this side. So that's the overall redox reaction. That's the half reaction, the reduction half and the oxidation half. How about the dichromate? Dichromate ions oxidize iron 2 ions to iron 3 ions, and the dichromate becomes a chromium 3 plus. This looks similar to the dichromate question I had earlier, but now I'm going to involve but I'm not going to do it by inspection. The iron 2 plus to iron 3 plus is really simple. I just say, well, iron 3 plus is too greatly positive, so I add an electron to this. This iron 2 plus must be losing 1 electron. I should slow down. It's getting all excited. But the dichromate, Cr2, goes to the chromium ion 3 plus. And you say, well, what happened to the oxygen? Well, I just didn't include it. Yeah, but I better go ahead and include it. 2 chromiums. So put a 2 here, put a 2, take this equation, I rewrote it with the 2. But you don't have to rewrite them each time, you just fudge it left and right and add things on the left and add things on the right as you need them. Then the oxygens, it seems like there's 7 oxygens on this side that are unaccounted for on the right hand side. So I go ahead and add 7 waters on this side because it's happening in water, and so water could partake or be created. It's a product or a reactant as you need it. So 7 waters make 7 oxygens. That gives me 14 hydrogens. 7 times 2 is 14, so I wave my magic wand and add 14 hydrogen ions over here. Many of these aqueous phase redox reactions happen more efficiently and better in an acidic solution or a basic solution. But I always do it as if it's acidic. In the end, I might have to change my story. But for now, let me pretend like it's an acidic solution. And now, this side has 2 times 3 is 6 pluses. This side has 14 pluses and 2 minuses for a total of 12 pluses. I add electrons to the side of the equation. That's 2 greatly positive. So this is 12 pluses compared to 6 pluses on the right of the arrow. So I need to add some electrons over here. So I add 6 electrons to bring this down to a 6 positive to balance that 6 positive. I could also tell I was going to need electrons on the left-hand side because this equation is an oxidation. The electrons are on the right-hand side. So if the electrons are on the right-hand side here, they have to be on the left-hand side here. But I didn't know it would be 6 until I figured out the charge balancing thing. So, question, how do I make 1 electron lost match with 6 electrons gained? Oh, I know. I'm going to take 6 of these and 6 of these and 6 of these to make 6 electrons lost match up with 6 electrons gained. Then I can add the 2 equations back together. These 6 electrons on the right cancel these 6 electrons on the left. And there's the overall, so whatever's left over and didn't cancel out is left over in your overall, hopefully balanced redox, aqueous phase redox reaction. And you can check them all if you want. 6 irons and 6 irons and 2 chromiums and 2 chromiums and 14 hydrogens and 14 hydrogens and 7 oxygens and 7 oxygens. 6 times 3 is 18 positives and 6 more positives is 24 positives. Is that right? I think that's right. I got 12 positives and 14 positives and 2 negatives. That's got to add up. Check it if you don't believe me. Here's another one. Permanganate. Permanganate's a strong oxidizing agent. It's going to oxidize lead into lead 4 plus. So that's simple. The oxidation is simply the lead goes to lead 4 plus and loses 4 electrons. But the permanganate's not so simple. It's done in an acidified solution. So I know some water is going to be involved here. I know some acid ions going to be involved here. So let me go to it. So I say the permanganate goes to manganese 2 plus. Can't just dump the 4 oxygens. I got to get 4 waters over here. That creates 8 hydrogens on the right. I got to get 8 hydrogens on the left in the form of the hydrogen ions, so acidic thing. Then I have 2 positives on the right. I have 8 positives and 1 negative. That adds up to 7 positives on the left, which is 2 greatly positives, 2 greatly positive. So I add some negatives to this side to make the charges balance out. Then I see 5 electrons gained compares to 4 electrons lost. How do I make a 5 gained and 4 lost match up if I hope to make these two half reactions match together? And the answer is you take this whole mess times 5. What? I should just erase one of those 5s. That's a boo-boo. Just take it times 5 once and take this whole mess times 4. Of course, that would give 5 leads and 5 lead to 4 pluses and 20 electrons. Take this times 4, take this times 4 and you get 20 electrons. 20 electrons lost, 20 electrons gained. Oh my goodness. You're telling me that you could balance this by inspection? Maybe you could, but I think the method of half reactions, once you get the hang of it, is much simpler. Here's another example. I might just let you look through this one on your lonesome. Peroxide goes to hydroxide, and the chromium hydroxide complex goes to the chromate ion. Whoa. Very interesting. Yeah, I'm going to let you look through that one on your own. See if you have any questions. No, I'm not. Is this the last one I have? No, it's not. Well, I better go over this one. Alright, let me slow down. So here's peroxide and here's hydroxide. This is a confusing one. This side has 2 H's, that only has 1 H and 2 O's and 1 O, so I'm going to just simply put a 2 there. That gives me 2 O's and 2 O's and 2 H's and 2 H's. But then this side has 2 negatives, so I better add 2 negatives over here. Peroxide gaining 2 electrons becomes 2 hydroxides. The complex CrOH4 minus becomes chromate. What do I have? 4 oxygens on this side, 4 oxygens on this side. That's lucky, but I also have 4 hydrogens over here, so I better get 4 hydrogens over here. Then this side is 2 greatly positive because this side's a single negative, and this side has 4 positives and 2 positives and 2 negatives. That gives me 2. Is that right? 4 positives. I think that's wrong. Get out of here. No, that's right. No. Yeah, okay. So 3 negatives. 3 negatives. And 2 negatives is 5 negatives, and 4 positives makes 1 negative to balance that. No, 1 negative. So then how do you make 3 lost match with 2 gained? You multiply one of them by 2 and one of them by 3, yeah? So how about I multiply this one times 3 to get 6 electrons gained, and multiply this one times 2 to get 6 electrons lost. Then I add them together, 6 electrons cancel here and here. That's all the cancels. It looks like kind of sort of maybe a mess. Oh wait, that's interesting. I have 6 OHs here and 8 H pluses here. Guess what 8 plus and OH minus make from your chapter on acid-base chemistry? They make water. So 6 OHs here, and these 6 of these make 6 waters. And so that's 6 waters. But you know what? I wanted to show you this one because what would happen if you, as the assumption was up here, weren't doing it in acidified solution? You could just as easily now change the story to basic. All you do is you add OH minus to this side, the side that has hydrogen ions, because you're not doing it in an excess acidified solution, you're doing it in a basic solution. So this sounds like hocus pocus, but you really can do it successfully. Say, well, I'm just going to add 2 OHs to this side to make 2 waters. I also have to add 2 OHs to this side. Let's see. So this makes 2 OHs, 2 waters, but I already have 6 waters here, so I guess that adds up to 8 waters. And I still have the 2 OH minuses on this side. Oh, this is crazy, I tell you. Yeah. Here's another example. I think I'll let you work through this one if you want to look through it, think about it, balancing half reactions. And I think on this one as well, I said, well, what if in the end we didn't have hydrogen ion? What if we weren't doing it in an acidified solution? So I added 4 OHs and add 4 OHs, see what cancels. Phew! Not only am I tired of talking, you are even more tired of listening. So thanks for watching, guys. See you in class.